So this is our second look at the prime number program, and we want to look at making things more efficient. So the first thing is, let's run this and just see how we're going to measure efficiency. So if I go in here and say, well, we enter a number to see if it's prime, I put in, say, 33. It says 33 is not prime. Notice Dev C++ has kind of this built-in thing when you compile it that measures the number of seconds it took to return value 0. Now 13.36 seconds, it didn't take that long to calculate. It was actually pretty quick, but I delayed in inputting the value. So we really don't want to be measuring how long it takes the user to input things. We want to take that kind of out of the equation. So what we'll do is go ahead and put in our value as part of the program. So when we compile and run it, it just does that automatically. And we're going to look at bigger numbers here. So let's go ahead and put in a 10-digit thing. And remember, we can use the single apostrophe to kind of denote this so we can see exactly what number we're dealing with. So every 3, we can't put commas in here, but we can put the single quote just to kind of be able to read exactly what that number is. Okay. Now, since we're putting that number in, we won't need the output and input statement here prompting the user to input things. So we'll just comment that out. And then we'll compile and run this and see how long it takes. So I'm going to go ahead and execute, compile, and run. And in our results, we find out that the number is not prime, but notice it took us just slightly over 37 seconds to come up to that conclusion. So let's look at a way to maybe make this a little more efficient. If you remember from last time, our loop setup was going from 2 up to the number we're checking, and we're going through here. And remember, we said as soon as it finds one of those numbers in between that's evenly divisible by 2 up to 1 less than the number, as soon as you find something evenly divisible, it's got more factors, so it's not prime. So we set is prime to false. But we can uncomment this break. In other words, the first time we find out it's false, we should be able to stop processing and not check all the other numbers, because as soon as one other factor's in there, we know it's not prime. So let's execute that and see if we get any change in performance. And sure enough, less than a second to find out that that number's not prime. Okay, so you might be wondering, well, what was the case there? So if we wanted to find out exactly what was going on, we can add an output statement here. Go ahead and do cout, and I'm going to say the number itself was divisible by, and what it was going to be evenly divisible by is going to be I. So I'm just going to output I, so we know what the first factor was that caused it to break. Okay, so I'll go ahead and output that and put an inline, and let's compile and run this and see. Some of you may know by looking at this number what the first divisible number might be, but let's find out. We'll compile and run this, and you can see that the first number that came up it was divisible by was 3, so that made it not prime. We didn't really need to check all the other values. So now if we wanted to see all the different culprits here, we could take out the break again so it doesn't break. If we compile and run this, again it's going to take a while, but we'll start to see all the different divisors that are evenly divisible and that number pop up here. So still takes some time, but you get all the stuff that's divisible, which we really are not interested in, because as soon as we find the first one, it's not prime. So just a way to put little inputs inside your program to do some checking to see what's actually going on, you know, self-check sort of stuff. Okay, so it took a little bit longer this time because we're outputting stuff to the screen. So it took about 40 seconds, and we'll do that. So let's leave this break in because that was a good improvement. One other question might be, what if I'm running a compiler that doesn't have that built in? So another way to check this is to include another library, and we're going to include Chrono. And what we can do is check the start time and the stop time. So if we jump down to the beginning of our process, I'm going to create a variable called start time, and that's going to be equal to std : chrono : high resolution clock : and now. So we're going to capture the current time, and then down at the end of our process we're going to do the same thing, except we're going to call the variable stop time equals same thing, std : chrono : high resolution clock now. So we've captured the stop time, and now we need to take the difference between the two. So we're going to declare a variable here for duration, and we're going to set it to a double with the resolution as milliseconds, and we're going to call that runtime. Okay, and we're going to set that equal to, and we're going to subtract the two, so we're going to take stop time minus the start time, and that should give us the difference between those two. And then we'll just add an output statement to show that on the screen. So cout, the runtime was, and we'll do runtime dot count, okay, is the actual duration between the start time and the stop time, okay, and we'll divide that by 1,000 because remember we had milliseconds. Since our measurements were more reasonable in seconds, I'm just going to divide by 1,000 so I can say we're outputting in seconds, and then we will run this again just to compare our clock to the compiler's clock. Okay, and without the break in there, it's pretty quick, pretty close to the same thing, under a second. This is more of a tenth of a second, but more processes are in there declaring variables. So it gives you a pretty good frame of reference for that. So let's go back out, and we will put the break back in. And I'm also going to comment out the divisible by. We don't really want to see all the divisibles, we just want to see the result. And remember, we're still using that large number. So let's run this again and see what our time duration says. Okay, so with a little bit of fast forwarding, we end up with pretty close to the same thing. Again, their process is a little longer because more of the program is in there. 38 seconds, and our timer says 37 seconds and a little bit. Okay, so we get pretty close, within about a second's worth of time between the two. So if you don't have this built into your compiler, you can add, using Chrono, that check to check the duration. Okay, so we probably do want to keep the break in there. That runs much faster. If we compile and run that, again, it's going to find out pretty quickly that it was not prime, right? It gets 3, which is like the second thing it checks. Now that works great if it's not a prime number, but for cases where we might have something that could be prime that's still a large number, this break is not going to help us. So let's execute that. And after a little bit of processing and skipping ahead a little bit on the video, we see that it takes quite a bit of time to look at this because it is prime. It's not going to get to jump out when it finds one of those factors. So 116 seconds. So next time I think we'll look at is there any way we can make this prime number checker any more efficient than it already is.